Can you see the material? Hello?
Yes, ma'am, we can see the material.
Okay. So in the last class, we are discussing one example where initially we assume that the random variable will assume discrete values. And from the concept of discrete random variable, we assumed a few things, and finally we saw that from the concept of discrete random variable, we can go for the concept of continuous random variable. And also we have seen that in the limiting condition, if we consider a continuous random variable, then the distribution functions will become continuous in the limiting condition, right? So when the distribution function will be a continuous one, then the random variable is certainly a continuous one in nature. So this is the cumulative distribution function of a continuous random variable. This is a continuous function, as we can see, and like discrete random variable, there will be no stair-step kind of discontinuities. Okay, so from the above figures, or we can even refer to this particular figure, so we can define these probabilities, we can define these events as well as the probabilities associated with the events. The first event is that the random variable will assume values within this range. That means the x will be greater than a and will be less than equal to b, and the probability of that can be computed with the help of this relation. That means this is the distribution function or cumulative distribution function. So this probability will be equal to fb minus fa. For recapitulation purpose, we know that fb, this distribution function, is probability distribution function or cumulative distribution function, implies that x, the random variable x, is less than equal to x or less than equal to b for this particular case. For this particular case, the random variable x will be less than equal to a. So from the difference of these two, we can ascertain the probability of this one. And since we are discussing a continuous random variable, hence the random variable will assume a specific value, say b. That probability will be equal to 0, that we have already studied, and that can be mathematically established with the help of this relation, where if we extend this particular concept for ascertaining the value of this random variable, a specific value of the random variable, then this relation will be equal to fb minus fb minus, since it's a continuous function. Now, since it's a continuous function, hence these two values are same, and hence the random variable, a continuous random variable, will assume a specific value will be equal to 0. So far we have discussed distribution function or cumulative distribution function, and from the notion of distribution function, now we can define probability density function. So in general, we term these two functions as distribution function and density function. So what is the notion of density function? Let's consider this situation, that is probability that the random variable will assume values which are certainly greater than minus infinity and less than x plus delta x, where delta x is very small increment in x, right? So this, as per the convention, can be written as the distribution function fx, and fx within the argument will be x plus delta x, x plus delta x. So this can be written as fx x plus delta fxx, right? Where delta fx again is a small increment in the distribution function. So from this we can write that delta fxx is equal to this minus this. So fx x plus delta x minus fxx. Now delta fx by delta x, if you divide this equation by delta x, then we'll get delta fx by delta x is equal to, this is the numerator part, divided by delta x. And in the limiting condition, when delta x is tending to a 0, then from this we'll get, this can be written, this relationship can be written as dfx dx is equal to limit delta x tending towards 0, the numerator divided by delta x, and the right hand side is written or is defined as this probability function, where this probability function or the first derivative of the distribution function is defined to be the density function, right? And by it's a general convention that the distribution function is denoted with the help of capital letter, whereas the corresponding density function is denoted or with the help of a small letter small f, and this is capital X denoting the random variable, and this is the range, that is this is basically the value that this random variable can assume, right? So dfx dx is equal to, or the first derivative of the distribution function with respect to x will result in the density, corresponding density function. Clear?
Yes, ma'am.
So from this density function, from this from this distribution function, very easily we can draw the corresponding density function, and the density function will look like this. I guess I don't have to explain this, because the distribution function, we know the distribution function, we know the nature of the distribution function, right? So the area under this density function, area under this curve, this area will give us the probability that the random variable x will assume a value which is less than equal to this value x1. So the probability of this event is equal to the area under the density function. Now already we have discussed that in case of distribution function and for discrete random variable, we saw that the distribution function actually contains stair-step kind of discontinuities. So to represent that particular fact, we can represent the distribution function in this form, that is summation of all these probabilities, that means x is equal to xi, x is equal to xi, and to represent that stair-step kind of discontinuity, we introduce this unit step at this particular discrete points where x is equal to xi's. So from this we can write down the density function. You see, if we take the first derivative of this with respect to x, then the density function will be equal to summation of all these probabilities, that is probability x is equal to xi. Remember, we are discussing discrete random variables, and this unit step will now change to delta, that means impulses at this discrete points. So the density function for this particular example, where we considered the discrete random variable, the corresponding density function can be drawn like this, right? At 0, the value was, this is the value was, this is a probability was probably 6561, right? So from this diagram, it's clear that, look at this expression. So from this expression, again, it's clear that fx, the density function, also gives us some probability. Now let's consider a continuous random variable corresponding to the angular position of a pointer after it stops, right? So this could be any angular position between 0 to 2 pi. If we consider a will, and if we rotate that, and if we assume that a pointer is attached with the will, so we know that the pointer can stop anywhere between 0 to 2 pi radians. Okay, so the probability of any particular position is 0, since this event will be described with the help of a continuous random variable. So we assign a probability to the event that the position of the pointer stops within a continuous range of values, say between 0 and theta radians. Number one. The second assumption is, if you assume that all positions are equally likely, naturally it's quite an obvious assumption. So all positions are equally likely. So then we can assign the probability in this manner. That means x will be the random variable, the continuous random variable will be less than theta and will be greater than 0, will lie within this range, is equal to 1 by 2 pi multiplied by theta, where theta is varying from 0 to 2 pi. Do you agree? Then we can plot the cumulative distribution function in this manner. So this is 2 pi. So you see, this is the relation. So we get a straight line starting from the origin. Along this axis, we are plotting theta. Along this axis, we are plotting the value of this probability, that is x less than equal to theta. Now, after this point, it will be 1 naturally, since we are discussing cumulative distribution function, and hence the total probability will be 1. Now, from this, one interesting thing is that we can note from this plot is, though we are considering a continuous random variable, in this particular case, in this distribution function, we see that there is a sharp change in slope at this particular point. Okay. Anyway, now if we want to plot the corresponding density function, then we'll have to take the first derivative, and obviously the density function will look like this: a step followed by a negative step to stop this one. So the value of this will be 1 by 2 pi at this point. Again, along this axis, we are plotting theta, right? So the density function will look like this. So probability that the random variable can assume a value within this range will be given by this area under this density function. And the thing is, why do we call it a density function? Distribution function is quite obvious, because we are showing the distribution of the values of the random variable, possible values of the random variable vis-a-vis, or probabilities of the values of the random variable vis-a-vis the possible values of the random variable, how the probabilities are distributed with the values of the random variable. So that's why the name, the distribution function. Now, why do we call it a density function? So you see, at this point, if I consider this point theta 1, then we can write that fx, this is the value fx at this point. So fx theta 1 into delta theta will give us this area is equal to area. So from this, we can write this probability to be fx theta 1 is equal to area by delta theta. Area by delta theta. So just some form of abstraction with the help of which we can say that this area is now densed within delta theta, within this width. This area is densed within delta theta, within this width, and hence this function is named probability density function. Right? So this is some form of density, area divided by the width. So this will give us some form of density. Clear? Do you have any question?
No, ma'am.
Now, properties of density function. Since we know that the density function also gives us probability, hence the fx, this value will be certainly greater than or can be equal to 0, cannot be less than 0 for all x. And fx, that means this probability will be greater than equal to 0. And the area under this density function, if we vary from minus infinity to infinity, so this integration signs gives us the area under this curve, that will be equal to 1. So what is this? Nothing but the total probability. That means probability that the random variable is assuming a value, assuming values within the range from minus infinity to plus infinity, right? So obviously this value should be equal to 1. Now if x1 can be written as, we know that the first derivative of the distribution function is the density function. Hence the distribution function in terms of density function can be written in this form, integration minus infinity to x1 fx zeta d zeta, which is equal to probability, that is the random variable is assuming values which are less than x1. So this is quite simple. This is another form of representation of the distribution function. We can represent density function as the first derivative of one of this, or we can represent the distribution function as the integration or area under this density function. And from this we can write this one, that is fx equal to probability x less than equal to x will be given by this, and the probability that the random variable will lie within a particular range defined by this, that means x is greater than x1 but less than equal to x2, that means it's including this value x2 will be given by integration, and now the limits will be from x1 to x2, right, fx dx. So this will come directly from this expression which we have discussed right now. From this one. So just let's have a look. Proofs of these properties are easy. Property 1 and 2 require that density function be non-negative and have an area of unity. These two properties can also be used to test whether some function, for example, gx of x, can be a valid probability density function. This is important. This is very important. So if you want to test that whether a function of x is really a valid density function, then we'll have to test these two properties, and if these two properties are satisfied, then we can say that yes, it's a valid density function. And also we have discussed for distribution function, the properties were listed, and the properties, I guess 1, 2, 4 and 6, those were important, and we'll have to test all those properties to find out whether a function of x is a valid distribution function or not. And property 3, as I said, is a different way of representing this particular equation. Property 4 relates the probability that x will have values from x1 to x2 including x2. Now, existence of density function. So we know that this is the definition of the density function. So if the derivative of fx exists, then we can say that the density function will also exist. So as we have already seen, there may be places where the derivative is not defined. For example, a continuous random variable will have a continuous distribution fx, but fx may have corner points, as we have seen. Point of abrupt change in the slope. This is the example. So for such cases, we plot fx, the density function, as a function with step type discontinuities, as we have already seen. And for a discrete random variable, we know that this is the expression which shows the distribution function, and for this step kind of discontinuities, the density function can be represented with the help of impulse functions. This is one representative figure. Now, this is your assignment. Please note, this is your assignment. So we'll test a function gxx to find out whether it's a valid density function or not. Then we'll integrate this function, right, within proper limits to find out that the result of integration, the function which is basically the result of the integration, whether that is a valid distribution function or not. This is your assignment. You'll have to solve this problem. So this is the nature of the density function. So this is the plot, not density function. This is a function, basically a function of x. Along this axis, we are plotting small x, right? So this is a function of x. This is the center point is denoted by x0. So this point is x0 minus alpha. This is x0 plus alpha. Density function from this, if you find that this is a valid density function, then from this you'll have to plot the function which is basically a result of the integration of this particular function. Then you'll have to plot it. Then you'll have to test the properties, respective properties, and you'll have to establish the fact that whether the result of integration is a valid distribution function or not. Though a few steps have already been shown in this lecture, but it's your task to complete this assignment. Now, one thing is sure, the function, this particular function, if this is a valid distribution, density function, then area under this curve will be equal to 1, that we have seen, right? So area under this curve should be equal to 1. So this is basically the hint. So from that, what will be the area of this area under this curve?
A into alpha.
A into alpha. That means the value of A should be equal to 1 by alpha, right? Since the area under this curve should be equal to 1. So from the nature of the plot given, we can write down the expression of gx, small gx, for this regions. So 3 regions. This is one region, This is the second region and this is the third region. So once you obtain, it's very simple, once you obtain the expression for gx, you perform the integration and hence find out whether this resulting function, which is also a function of x, whether that is a valid distribution function or not. And justify that with sufficient mathematical derivations. Now, since here we are discussing distribution function, density function, etc., all these terms, we are discussing random variable. So, for example, as an example, in this chapter, we'll discuss one very important distribution or density function, which is named as the Gaussian distribution or Gaussian density function, right? Other density function, there could be other density functions as well. The density functions, distribution functions can be classified as discrete distribution functions or discrete density functions or continuous density functions. So under discrete distributions, we'll study Bernoulli's trial, then binomial and Poisson. And under continuous distribution, we'll study exponential, gamma, chi-square, Erlang, uniform, that is also very important, etc. But the distribution and density functions will be discussed in detail in the next chapter. Just for an example, we'll discuss the Gaussian distribution function in this particular chapter. Have you studied Gaussian distribution function? Have you ever studied Gaussian distribution function?
No, ma'am.
Okay, so let's start with the density function. So in case of a Gaussian density function, the density function will have a loop which is equal to this fxx is equal to 1 by root over 2 pi sigma x square e to the power minus within bracket x minus ax by a, sorry, minus in the numerator it's within bracket x minus ax whole square by 2 sigma x square. So if we draw the density function for different values of x, we'll get this kind of a bell-shaped function. So this kind of a bell-shaped function is called a Gaussian distribution function, and under certain assumption, this Gaussian distribution function can also be denoted as normal distribution function. Right? Now, at this very moment, we'll not be able to appreciate the exact meaning of ax and sigma x. Rather, I guess you have heard these terms, expectations or mean and standard deviation or variance.
Yes, ma'am.
So in this case, you see, this is the center point of this bell-shaped curve. Why I'm calling it a center point? Because at this particular point, when x is equal to ax, the bell-shaped function is reaching its minimum, maximum. So this is the maximum value, right? And so that's why we'll see that this value is generally called to be the mean value of this density function. Mean value of this density function, number one. Number two, what is the nature of what is the nature of this bell-shaped function? You see, this is one representative figure, right? Another bell-shaped function, just follow the cursor since I don't have the board. So another bell-shaped function could be drawn like this. That means a narrower one. Do you get my point?
Yes, ma'am.
a narrower one, whether it's an this bell-shaped function is a wider one or narrower one, right? How to get that estimate? That estimate will get from this value ax, which is the center point, and from this value sigma x. So here this are the 2 points. One is ax plus sigma x, and at the other side of the center point we are marking another point, which is ax minus sigma x on this x-axis, right? And this is the maximum value, which is given by 1 by root over 2 pi sigma x square. And at these 2 points, these 2 points are symmetrically placed, and at these 2 points we see that the value, the maximum value, the peak value has dropped to a value which is given by 0.607 divided by 1 point root of 0.607 divided by root over 2 pi sigma x square. So 1 by root over 2 pi sigma x square was the maximum value. So 0.607 times this peak value we are getting at these 2 points, right? So that will give us the information about the spread of this bell-shaped function. Okay. So that is the significance of sigma x, and when we'll study standard deviation and variance, we'll learn that the sigma x is known to be the variance of this density function. Now from this distribution, from this density function, and moreover, one thing we should mention that the sigma x and ax are real constants. And from this bell-shaped function fx, if we integrate, then we'll get the corresponding distribution function which have a look like this. So this is the point corresponding to the center point ax, and this is the point, these are the 2 points lying at the side of this ax. One is ax plus sigma x and the other one is ax minus sigma x. So this is the value at this point, and this is the value of fx at this particular point, and after a while it will approach 1. So this type of distribution function is, or this type of density function is known as the Gaussian density function. Obviously from the plot itself, it's clear, from these 2 plots, it's clear that the corresponding random variable x, that is a continuous random variable, and the Gaussian density or distribution function is a continuous density or distribution function. Right? So ignore this part. Ignore this part. So its maximum value is given by 1 by 2 pi sigma x square to the power 0.5. That means square root of this. That occurs at this point x is equal to ax. Its spread about the point ax is equal to ax is related to this sigma x, and the function decreases to 0.607 times to its maximum value at these 2 points. So we'll discuss Gaussian distributions in detail when we'll discuss additive Gaussian noise. The Gaussian distribution is really very, very helpful for modeling some particular type of noises. Just a second. The Gaussian density and distribution functions are not limited for modeling of noises, but this density or distribution function can be used for representing very many random processes, random situations that we encounter in real life. Just let's go very fast through this section. Gaussian is the most important. We can't say the most important of all densities, but it's a very, very important one. The importance stems from the accurate descriptions of many practical and significant real world quantities. For example, voltage across a resistor at the output of an amplifier can be random. Noise voltage. You heard about thermal noise, isn't it? Do you know what is a thermal noise? Hello?
No, ma'am.
Okay, so we'll discuss that when we'll be discussing noise. Um, Voltage across a resistor at the output of an amplifier can be random. So the voltage will be a noise voltage, will not be a deterministic one. It will not be a deterministic one, it will be a noise-like voltage because of the presence of random current, which is the result of many contributions from other random currents at various places within the amplifier. It's not, I know it's not clear. Let's see the next point, random thermal agitation of electrons. That you know. Thermal agitations of electrons are basically random in nature. The motion of the electrons are random in nature. That we know from the knowledge of basic physics. So random thermal agitation of electron causes the randomness of various currents. So this type of noise is called Gaussian noise, as the random variable representing the noise voltage has a Gaussian density. So the random the voltage distribution is like this kind of a bell shape kind of or does have a bell shape kind of nature, and that's why we represent that noise like voltage with the help of Gaussian density function. So this already we have seen is the density function for the Gaussian random variable, or we can say in other words, a Gaussian random variable will exhibit this density function given by this expression, where typically x is the mean of the density function and sigma x is the standard deviation associated with the density function. So from this, we can write the distribution function, corresponding distribution function, to be equal to 1 by 2 pi sigma x square under root, and we'll have to integrate this, that we know. So integration from minus infinity to x, and this part within the integration will be this part, and we have only changed, since the upper limit has been taken to be x, hence we have changed the variable. So this is minus within bracket zeta minus ax whole square by 2 sigma x square d zeta. Clear? Do you have any question?
No, ma'am.
Now the problem is this integral has no closed form solution. So either we'll have to go for some numerical method, we'll have to employ some numerical methods, or we can determine the value of this integral with some, or with the help of some approximate methods. Okay. So here we'll discuss some approximate methods with the help of which we can find out the value of this, right? Because we want to know that what is going to be the probability that the random variable x will be less than equal to this small x. So here you see we do have two parameters which actually dictates the value of this integral. One is this ax, the other one is this sigma x. So what can be done to make the results generally available? We develop a set of tables of fx x for various values of x with ax and sigma x as parameters. That means if we fix the value of ax and if we fix the value of sigma x, then we can prepare a table where we can provide values of fx x vis-a-vis x, different values of x. Now, what is the problem? If we go for this kind of solution, what is the problem? For different sets of ax and sigma x, right? We'll have to use a different table. That means if we go for this kind of solution, right, actually theoretically we'll be requiring infinite number of tables, infinite number of such tables as the sets ax and sigma x, combination of ax and sigma x could be infinite. That is the problem. So what could be the solution? Yes, we'll go for some approximate method, and here we'll try to normalize. We'll try to get a normalized expression for this integral. Okay. So if we go for some kind of normalization, then it might be possible that one single table would suffice to find out the value of fx for a given x. So a better approach is possible where only one table of fx is developed that corresponds to a normalized or specific values of x and sigma x. The first step to normalization is if we assume x to be 0 and sigma x to be 1. So if we assume x to be 0, then the distribution of the density function will be said to be a zero min density function. So a zero min density function, zero min Gaussian density function will again give us another density function, which is a normal, or distribution function will give us a normal distribution function, which is also a very, very important one. The corresponding, so if we assume ax to be 0 and sigma x to be 1, then the expression for fx will be, since sigma x is equal to 1, so this part will be 1 by root over 2 pi, and the integration, the limit of integration is remaining same from minus infinity to x. Now this one will be e to the power minus zeta square by 2 d zeta, as ax is equal to 0, as ax is equal to 0. Could you please note down this expression?
Yes, ma'am.
Please note it down. There is a minus sign over here. There is a minus sign.
Noted, ma'am.
Okay. So if ax is equal to 0, then that expression will reduce to this particular form, right? Now, one thing is clear from this density function, that this density function has a property of symmetry. There's a symmetrical one. Okay. So please remember that the density function is a symmetrical one. It does have the property of symmetry. So for negative values, actually the table that we get, I'll give you the table. The table that we get, the table is generally available for positive values of x, for x greater than equal to 0, for positive values of x. But if x is negative, then we can find out the value of the probability that if the argument is minus x, that means the probability p that the random variable x is less than equal to minus x. That probability can be computed with the help of this relationship. That is, f minus x will be equal to 1 minus fx because of the symmetry about 0. Let's see. So this is the plot, right? This is a value a. The value of x at this point is a. So area under this is the density function, as you can see from this. So the area under this curve up to this point, from infinity, minus infinity to a, is nothing but our fa, or for the timing we are writing it as phi a. So area under the curve will give us the distribution function fa, which is equal to probability that x is less than equal to a, where a is positive, right? Then 1 minus, just ignore this for the time being. So 1 minus phi a, 1 minus phi a is this particular area, the unshaded one, unshaded portion, right? And because of the symmetry about if ax is equal to 0, so because of the symmetry about this fx axis, if I take a point somewhere over here where the value of x is, the absolute value of x is again a, so the value is minus a, then the area from infinity to that particular value, x is equal to minus a, will be same as this area. Am I clear? Do you agree?
Yes, ma'am.
So this is the area. At this point, the value of x is minus a, and this is the area where the value of x is varying from minus infinity to minus a. And because of the property of symmetry, we can see that this area is equal to this area. Hence, we can use this relation to find out the probability where the value of x is negative. So f minus x is equal to 1 minus fx. Why this relation is required? As I said, the table is generally available for positive values of x. Now, actually our aim is to convert this expression of the distribution function to this form, right? Which is basically the normalized form, as already we have seen. So for that, what we are doing, we'll go for a variable change, and let's define a new variable u, which is equal to zeta minus ax by sigma x. So that means sigma x into u is equal to zeta minus ax. So if we go for this kind of variable change, then this limit will change. This limit will change, and now this limit will become x minus ax by sigma x, right? And this sigma x part, we can take out this sigma x square, and here we can write 1 by sigma x. And you see here, sigma x into du will be equal to d zeta. D zeta. Hence, I guess it's written somewhere. Yes, sigma x du is equal to d zeta, right? And this is the new variable. So we'll get, this is the new limit. And so fxx can be written as 1 by root over 2 pi. Within the integration part, we'll have 1 by cx, sigma x e to the power minus u square by 2 sigma x du. That means we are getting 1 divided by root over 2 pi integration minus infinity. Now the upper limit has changed. It's now x minus ax by sigma x, and within the integration sign we are getting e to the power minus u square by 2 du. So this fx now can be, since this is the limit, so it can be written as fx x minus ax by sigma x. Yes or no?
Yes, ma'am.
Yes, ma'am.
Is it clear absolutely?
Yes, ma'am.
So we can use this expression, and we can convert this variable into this variable, and then from the table we can compute the value of the probability as required. Now the function fx can also be evaluated by another approximate method. What is that? Let's see. So let's write fx as fx is equal to 1 minus qx. 1 minus qx. So 1 minus, if I considered this expression of fx, then the limit was fx is equal to 1 by root over 2 pi, and the limit of integration was minus infinity to x. Why? Because it was giving us the probability that the random variable x is less than equal to x. Now 1 minus fx, then the limit will simply change from x to positive infinity, isn't it? 1 minus fx, only the limit will change, and the limits will become now x and infinity. So integration x to infinity e to the power minus zeta square by 2 d zeta. Clear?
Yes, ma'am.
So this qx is known as q function, and this integral is very important. So if you take the honors paper in final year, if you take the honors paper principles of communication engineering, then you'll find that this q function, with the help of this q function, we can find out the performance or bit error rate. Bit error we discussed in the last class. So what is going to be the bit error rate for different types of digital modulation or digital communication scheme? Say, you won't be able to understand what is meant by modulation right now. So for assessing the performance of different type of digital communication systems, this q function is required. The q function is very, very important, and q function is used, it's called Gaussian integral, in different applications as well. So that this is, if we plot fx, then that is the plot of fx distribution function. So this is fx. If I consider the integration, the limits of the integration to be from 0 to x, from 0 to x, and so this part will give us the q function, right? And the limits of the integration will change from x to infinity. So that is our Q function. Now, just like fx, qx also doesn't have any closed form solution, but does have an excellent approximation given by qx is equal to, you can see this expression. So within the third bracket, we have terms like this: 1 divided by 1 minus a into x plus a into square root of x square plus b whole multiplied by e to the power minus x square by 2. Is this minus sign legible? Is the minus sign over here, is that legible?
Yes, ma'am, there is a small break between the two lines.
Yes, there is a minus sign over here. So e to the power minus x square by 2 divided by 2 pi when x is greater than equal to 0. And here this a and b are constant. Right? And we can have different values of a and b, but empirically it has been found that if we choose the value of a to be equal to 0.339 and the value of b to be equal to 5.510, then if we choose these two values for these two constants a and b, then qx will give us a very good or near accurate result of that integration, which is known as Q function or Gaussian integral. So with these values of a and b, the above approximation, this approximation is said to equal the true value of qx within a maximum absolute error of 0.27% of qx. That means the approximate value of qx can deviate from the actual value of qx at most by this percentage. So this is the minimum absolute relative error. These two values will generate minimum absolute relative error. So let's discuss one example. So we'll be able to learn how to use this Gaussian integral or this qx for evaluating fx. So let's assume a Gaussian random variable for which the value of ax is equal to 7 and sigma x is 0.5. So we have been asked to find out the probability of the event x less than equal to 7.3. That is the probability x less than equal to 7.3. So this is basically the value of the distribution function. So this is actually fx. What is going to be the capital fx? Fx is equal to probability x less than equal to 7.3. So how to find out? It's a bit hard to read. Can you see this? Probability x less than equal to 7.3 is equal to fx 7.3.
Yes, ma'am, we can see.
So probability x less than equal to 7.3 is nothing but fx 7.3.
Yes, ma'am.
So that is equal to fx. If I change the variable, that means x minus ax divided by sigma x. So that is equal to fx into 7.3 minus ax divided by sigma x, and we are getting a value f is equal to 0.6. Please check this value.
Yes, ma'am, it is correct.
So f 0.6, right? So that will be equal to, we know that that is equal to nearly equal to 1 minus qx So that will be equal to 1 minus Q 0.6. Right? Now to find out this value, so 1 minus, this is the approximate value. Already we have seen. This is the approximate value. So we'll take the values of A to be equal to 0.339 and B to be equal to 5.510. So Q 0.6 can be computed as 1 divided by 1 minus 0.339, 1 minus A into X, that is 0.6 plus A into root over X square plus B, that is 5.51. That was the expression, right? And that will have to multiply by this term. So e to the power minus 0.6 whole square by 2 root over 2 by root over 2 pi. So this part we don't have to perform any integration. We don't have to go for any numerical methods like whatever. So anyway, simply with the help of calculator, we can find this particular value. So it comes out to be equal to 0.7264.
And how accurate is this? I mean, the approximation.
I'm coming to that. And if we look at the table, if we refer to the table, then we'll find that F 0.6 is 0.7257, this value. So instead of getting 0.7257, we are getting 0.7264. So for this particular case, we can find out the absolute relative error, which is absolute means we are not considering the sign. This can be greater than this one or this can be less than this one. So we are considering the magnitude of the difference. So 0.7264 minus 0.7257 divided by this actual value, which is 0.7257. So if we convert it into percentage, we see that the percentage error is 0.096%, which is pretty less. And here we have seen that the maximum error, maximum deviation could be equal to 0.27%. 0.27%. So this is quite a good approximation, isn't it?
Yes, ma'am.
And the method has its own advantage because of its simplicity. Simply with the help of a calculator, we can find out this probability. Now, operations on random variable. Now we'll discuss some operations that are performed on the random variable. The first one is the expectation or expected value of a random variable. So let's first consider that x is a discrete random variable. Then the expected value ex is defined or can be found, not only defined, can be computed as, this is the notation, expectation of x is equal to summation of I is equal to 1 to n, where n number of possible realization of the random variable are possible. So summation over 1 to n xi, probability that the random variable x will assume a value which is xi. So xi is the one possible realization of the random variable of this discrete random variable x, and this is the associated probability. So if we sum all these terms, that means x1 px1 plus x2 px2, etc., then we'll get the expectation. So this is one kind of operation performed on this random variable. This is the operation. So conceptually, this is the average when an infinite number of trials have been carried out. So here we can apply the concept of relative frequency. So let's see. Okay, let me read out these lines. So this is actually a hypothetical average, which is also known as mean, average, expectation. A hypothetical average is called the expected value. It refers to what one would expect in a typical statistical situation, right? So while we are considering any game of chance or any statistical situation, what we would expect. So that is the expected value or average value. And why we are saying that the concept of relative frequency can be applied. So this quantity is referred to as either expectation or statistical expectation or mean or average. All these terms are used almost synonymously. So let's consider a discrete random variable with n possible realizations like x1, x2, xn. And let's assume that the corresponding probabilities are p1, p2, pn, right? So if we carry out n number of trials where n is quite large, n number of trials, then since these are the realization of the random variables and these are the associated probabilities, so in n number of trials, the x1, we would expect that x1 will occur with a probability p1 n number of times. So the occurrence of x1 will be given by p1 into x1 into n. Similarly, the occurrence of x2 is given by p2 into x2 into n. So let's sum up all these occurrences, that is p1 x1 n plus p2 x2 n plus pn xn n, right? So these are the outcomes, and if we divide this by the number of trials, that is the concept of relative frequency, number of trials, then we can expect that we will be getting some average value, some sort of average value or mean value, right? So n will cancel out from the right hand side, and hence the expected value or the average value or the mean value of the random variable is defined to be, or defined with the help of this expression. Clear?
Yes, ma'am.
Now, this will actually give us, for continuous random variable, this will give us the density function, right? So because this is the PMF or the density function for discrete random variable, so we can extend this concept for continuous random variable, and the expected value x is given by expectation of x. This is the operation being performed on this random variable, and that is defined to be integration minus infinity to infinity x into fx dx. So the first case, discrete case, when x happens to be discrete with n possible values xi having probabilities pxi of occurrence, then fx is given by this, that we know, and the expectation is given by this. For continuous random variable, expectation x bar is given by this. So expected value of a function of a random variable. This is the expected value of the random variable. Now we can define any function of the random variable and we can find out the expected value of the function of the random variable. So many useful parameters related to a random variable can be derived by finding the expected value of a real function g of x, right? So in that case, the expected value of this real function gx, expected value of the real function gx is defined as integration minus infinity to infinity gx fx dx, right? So for expected value of the random variable, it was x fx, and expected value of a function of a random variable where the function is gx will be given by integration minus infinity to infinity gx fx dx. So for discrete random variable, the expected value of a function of a discrete random variable will be given by summation. Only x will be replaced by gxi. So summation I varying from 1 to n gxi into pxi. And already we have seen the generalized form. Now, note that if gx is sum of n number of functions, gnx, so n number of functions could be g1x, g2x, gnx, right? Then the expected value of the sum of n functions of a random variable is the sum of n expected values of the individual functions of the random variable. I'll come to this point once again. Let's first see the derivation. So expected value of the sum of a few functions, gi's, right, where I is varying from 1 to n. So we can expand this sum within this bracket. So then if we remove the summation sign, so within this bracket we'll get g1x plus g2x plus gnx, right? So this is nothing but, the first one can be written as minus infinity to infinity integration g1x fx dx, plus the second one will be, as per definition, minus infinity to infinity g2x fx dx, so and so forth, right? So this one can be written as expectation of the first term, first function rather. This one is the expectation of the second function. This is the expectation of the last function, right? So expectation of sum of a few functions of a random variable will be sum of the expectation. So let's go through this point. Please note that if gx is sum of n functions, if gx is sum of n functions, then the expected value of the sum, expected value of the sum of n functions of a random variable is the sum of n expectation, sum of n expected values of the individual functions of the random variable. Just go through this point and go through this derivation and find out whether you have understood this or not. Is this point clear?
Yes, ma'am.
Okay. Now let's come to the concept of moments. Now moments can be again classified into two groups. One is the moment about origin, and the second one is, the second notion is called the central moment. That is the moment about the mean or the expected value. So so an immediate application of expected value of a function of a random variable is calculating moment. We are discussing the expected value of a function of the random variable, right? Now in this section we'll see that for finding out moments, we'll define moments right now. For finding out moments, we'll have to find out the expectation of some function, of a given function of the random variable. As I said, moments can be of two types, either about the origin, can be defined to be about the origin, or moments can be defined to be about the mean. The second moment is often called the central moment. So moments about the origin. When a moments about the origin is defined as a function gx, as a function gx is the function of the random variable which is given by x to the power n, where n can vary from 0 to 1 to 2, etc. When the value of this power is n, then the moment this, if we take the expectation, then we'll get a moment, and that moment is called the nth moment about the origin. So if we define the function of the random variable in this manner, x to the power n, x to the power n, n greater than equal to 0, then if we can compute the expected value of this function, then that particular expected value will be called to be the nth moment of the random variable about the origin. Clear?
Yes, ma'am.
So now we'll have to find out the expectation of this function. This is the generic form. So the moments about the origin are typically denoted by this letter small m, whereas the moments about the mean are denoted with the notation mu. This is convention, typical convention. So mn, that is the nth moment, will be expectation of this function gx, where gx is nothing but x to the power n. So as per definition, we know that this expected value will be an integration. The limits will be from minus infinity to plus infinity, fx, x into fx dx. Now here x is equal to, or rather gx into fx dx. Here gx is equal to x to the power n. Hence, the terms within the integration sign will be x to the power n fx dx. Okay?
Yes, ma'am.
This one. So this is the nth moment about the origin. So let's try to find out first the 0th moment about the origin. So the 0th moment about the origin, for that the value of n will be equal to 0, right?
Yes, ma'am.
So m0 will be equal to integration minus infinity to infinity fx dx. So what will be the value of m0? Area under this density function.
0.
So area under this density function, x to the power 0, x to the n is 0. So x to the power 0 means this is 1, isn't it?
Yes, ma'am.
So the integration will reduce to minus infinity to infinity fx dx, 1 into fx dx, right? That means area under the density function, and we know the total area under the density function is equal to unity. Can you recall?
Yes, ma'am.
So the 0th moment about the origin, you see, m0 is equal to e to the power x0 is given by minus infinity to infinity integration fx dx is equal to 1. The total area under the curve fx. Now let's now try to find out the first moment about the origin. That means the value of n is equal to 1. So m1 will be equal to e to the power x to the power 1. That means e to the power x. That means the right hand side will be integration minus infinity to infinity x fx dx as n is equal to 1.
Yes, ma'am.
So what is this? Nothing but the expected value of x, the mean value of x integration x fx dx, that is by definition or by derivation is equal to the expected value of x. Can you recall, or do I have to show the expression?
You can recall, ma'am.
So m1 is equal to expectation x to the power 1, that is minus infinity to infinity integration x fx dx, that is x bar, the expected value of the random variable. So in this way we can find out m2 second moment about the origin, so and so forth. Now let's come to the central moments. Moment about the mean value of x, that means the expected value of x, are called central moments, or moments about the average, or moments about the expected value, or moments about the mean, right, or central moment, and are given by the symbol mu n. They are defined as the expected value of the function. Now this function moment about the mean, hence the nth order function gx is represented as x minus x bar. This is the mean value. So x minus x bar whole to the power n. So instead of x to the power n, which was the definition of central moment after taking expectation, which was the definition of the moment about the origin after taking expectation. Now, while we'll be calculating the central moment, the function will become x minus x bar, and the nth, for calculating nth moment, the generic function gx will be x minus x bar whole to the power n. Clear?
Yes, ma'am.
So the nth order moment, nth order central moment, or nth order moment about the mean is given by expectation of x minus x bar whole to the power n, which is equal to minus infinity to infinity plus infinity x minus x bar, this is the expected value, x bar whole to the power n fx dx. The definition is not changing, only the function is changing. So from this, if you want to find out the zeroth moment, then it will be expectation mu 0 will be equal to expectation x minus x bar to the power 0, or in this expression it will be, this is equal to minus infinity to infinity x minus x bar to the power 0 fx dx. Again this term will be 1. So again the zeroth central moment, the value of the zeroth central moment will be equal to 1. Total area under the curve fx, or density function. Now the first moment, the first central moment, or moment about the origin, about the mean, is given by expected value of these two third brackets. So x minus x bar to the power 1, right? So this can be expanded as expectation of x minus expectation of x bar. Now expectation of x, that is expectation of this random variable x, will give us the average value or the expected value x bar, right? And since x bar is constant, hence expectation of x bar will result in x bar only. Okay, so x bar minus x bar will be equal to 0. So the first central moment, the value of the first central moment will be 0. Now we can prove this in another way. So mu1 is expectation of x minus x bar whole to the power 1. So As per this definition, it will be equal to integration minus infinity to infinity x minus x bar fx dx. Now we can break this this expression into two parts. One is integration minus infinity to infinity x fx dx, this part, and the second part is minus x bar integration minus infinity to infinity x bar fx dx, this part, right? Now we know the first term will be equal to the expected value of the random variable by definition. So x fx dx integration minus infinity to infinity will give us the expected value x bar. Now in this case, x bar is constant, mean value is constant, so we can take this out of this integration sign. So x bar integration minus infinity to infinity fx dx, and we know that that particular integration, this part, this integration, the value of this integration is equal to 1, as it represents the area under the total area under the density function, right? So it is x bar minus x into 1. So the value or the first central moment, the value of the first central moment will be equal to 0. Please go through the steps. So far, is this clear?
Yes, ma'am.
Okay. Today I'll stop at this particular point. Next class we'll discuss variance and skew. Do you have any question?
No, ma'am. We'll revise the whole thing once again. Then, if you have any questions, we'll ask in the next class.
Okay.
Ma'am,
Just,
can
just
you share the recording of the class, ma'am?
yes, I'll send you the recording. Let me close this. Don't leave the meeting.
Okay, ma'am.